In the year 1994, astronomers around the world were witness to a perhaps once-in-a-lifetime event. Stretched across the sky were 21 fragments of a massive comet that had broken apart. Each fragment big enough to cause unimaginable destruction, and all of them were on an imminent collision course. Thankfully for us, Earth was not in the crosshairs. Instead, these fragments were hurtling towards Jupiter at incredible speeds. Despite never touching the Earth, this comet would end up leaving a deep impression on humanity. And I would argue that the impacts of this comet easily qualify as the most significant extraterrestrial event of our lifetimes. This is the story of Comet Shoemaker-Levy 9. Some 20 years prior, at the start of the 1970s, it was a somewhat radical idea that extraterrestrial impacts could pose a threat to planets at all. At this time, the theory that an asteroid had obliterated the dinosaurs had not yet been formulated, and most astronomers dismissed impacts as incredibly rare curiosities rather than ongoing hazards. Veteran US astronomer Eugene Shoemaker, who had been studying meteor crater in Arizona, was not convinced by this, and he believed extraterrestrial impacts could potentially be a threat to the Earth. Shoemaker had by that point already worked for NASA for 20 years, and leveraging his experience secured funding for a new, first-of-a-kind program to map Earth-crossing asteroids. The idea was that if we could map asteroids before they showed up in our atmosphere, we would have more time to do something about them. While today cataloging asteroids is our main method of searching for potential impactors, in Shoemaker's time this was new and he was truly pioneering the field. In 1973, Shoemaker's program was able to go ahead at the Palomar Observatory in California, and he was able to book early but consistent successes and identify numerous risk-posing asteroids. Seeing these successes, in 1982 NASA expanded the program, and Canadian amateur astronomer David Levy, as well as Eugene's wife Carolyn Shoemaker, were brought into the team. Together, the three identified many asteroids and comets. It was a painstakingly slow and meticulous process of manually searching photographic plates taken by Palomar's telescope for moving dots in the sky. But over time, the process paid off. By the early 90s, the program was already accredited with the discovery of hundreds of objects and at least 8 comets. But it was their 9th joint comet discovery that would go down in history. It was 24 March 1993 when Carolyn Shoemaker was examining the photographic plates taken by the observatory's telescope over the course of last week when she noticed something peculiar. Stretched out across the plate was the wispy figure of a comet, and a pretty unusual one at that. While most comets have a distinct appearance with both a head holding the nucleus and a dusty tail trailing behind, this one appeared like a dense, linear bar which was over 50 arcseconds long and 10 arcseconds wide, and it only had a very faint, hazy tail. The object appeared with a magnitude of positive 14, which is roughly 6,000 times too faint to be seen with the naked eye. To Carolyn, it was immediately clear this was no ordinary comet she was looking at. The discovery was immediately forwarded to the Spacewatch program at the nearby University of Arizona, as part of standard procedure when a new object was discovered. There, its discovery was confirmed by James V. Scotty. The object, that would become known as Comet Shoemaker-Levy 9, was reported to consist of at least 5 trailing nuclei. This was highly unusual, as most comets only have a singular nucleus, but this one was clearly fragmented. In fact, later observations of the comet revealed that the number of fragments was much greater than the initial 5 suggested by Scotty, numbering at least 15. It was as if some massive force had torn this comet to shreds. The question was, what force could be strong enough to rip apart a comet? After the discovery of Shoemaker-Levy 9 was announced, it was Brian Marsden of the Central Bureau of Astronomical Telegrams who first noticed the comet's proximity to the planet Jupiter at less than 4 arc degrees, suggesting that, The comet is located some 4 degrees from Jupiter. The motion suggests it may be near Jupiter's distance. By May 1993, Marsden had enough observed positions to attempt to model its orbit, and was able to show the comet was not just close to Jupiter, but orbiting it. According to him, the massive gas giant had captured a solar orbiting comet some decades prior, and it had made a catastrophically close passage of the planet in July 1992, soaring as close as 42,000 kilometers above Jupiter's cloud tops. At this distance, the comet would have been well inside Jupiter's Roche limit, the innermost boundary around a body where stable orbits can exist, and as a result had its nucleus ripped apart by the giant's gravity, causing the observed fragmentation. Prior to this, Comet Shoemaker-Levy 9 might have been a several petagram mass object measuring between 1.6 and 2.5 kilometers across. But that was not all, as Marsden's models revealed the comet could make another close passage of the planet the next year. According to his models, there was a near 99% certainty that the fragments would pass as close as 45,000 kilometers of the planet's center, inside its radius, revealing an imminent impact in July 1994. When Marsden made the announcement that Comet Shoemaker-Levy 9 was on a collision course with Jupiter on 22 May 1993, it did not yet gather much mainstream media attention. This was the early 90s after all, and while the mainstream news focused on more trivial matters like the foundation of the European Union that same month, astronomy communities around the globe rejoiced as for the first time humanity would get to witness a major impact event up close. That said, due to the comet's fragmented nature, this would be no ordinary impact event, with just one big boom, but rather a series of sequential impacts spread out over a period of a few days. We would get to witness not one, not two, but up to several catastrophic impacts on Jupiter the coming year. Because the fragments were quite large, each impact had the potential to release up to 25 times as much energy as the entire world's nuclear arsenal combined, which back in 1994 was substantial. Or 400 times more powerful than the Tambora eruption of 1815, which, if you've seen my video on it, was no small explosion either. At this point in the 90s, we had no probes in the Jovian system. It is true the Galileo was launched and well en route, but by 1993 the planet had still remained relatively understudied. If we could witness the comet slam into Jupiter, it would help us uncover a plethora of scientific data about the planet. With that in mind, astronomers around the world scrambled to make sure humanity would be able to get a good view of the impacts. By October 1993, the probability of a Jupiter impact had risen above 99%, and very soon it became known that they would hit at latitudes 44 degrees south, some 3 to 9 degrees behind its dawn limb. This meant the impacts would occur on Jupiter's far side, which would be facing away from the Earth, and thus they would not be visible to astronomers. A bummer to be sure, but astronomers did not despair. By 1994 we had a number of probes and telescopes already in space, and we could point those at Jupiter in our stead. The Voyager 2 probe, at this point in time already well beyond Neptune, was able to look back at Jupiter and observe the impacts from a vast distance of 42 astronomical units. Then there was the Ulysses probe closer to home, which was also primed to observe the impacts. And of course, there was the Hubble Space Telescope, freshly repaired in 1993. And finally and most prominently, there was of course the Galileo probe, by this time well en route to Jupiter, which would be able to observe the impacts most closely from just 1.4 astronomical units or 210 million kilometers away. Even though the impacts would occur on Jupiter's far side, given the planet's fast 9.8 hour rotation period, the impact features they would leave behind would rotate within view of the Earth just minutes afterwards, so that even ground-based astronomers on Earth could observe them granted favorable weather conditions. So, while the actual impacts would not be directly observable to us, their aftermath would be clearly visible to us soon after. By December 1993, the probability that all of the fragments would impact Jupiter had risen above 99.99%. The first impact was expected to occur on 16 July of 1994, and then the other fragments would continue impacting Jupiter for a period of at least 6 days to follow. As the date of the first impact drew closer, the event started to gather more attention for the larger public. The events, which became known under the name Impact Week, drew more and more attention, as across the world news outlets would cover the spectacle with live broadcasts and daily updates. On 13 July, the Hubble Space Telescope imaged a train of fragments clearly as they hurtled towards the gas giant. It's a truly terrific picture if you know what you're looking at, and it makes me wonder if we'll ever experience something like this again in our lifetimes. In the final days before 16 July, all the telescopes and instruments at humanity's disposal were tuned to look at Jupiter as hype exploded. Some observatories even reported technical difficulties with their observations due to overcrowding, as masses of people showed up to watch the events. On the 16th of July 1994, at 2013 UTC, the first of Shoemaker-Levy 9's fragments came crashing down into Jupiter's atmosphere. This fragment, dubbed Shoemaker-Levy 9A, with the next one being Shoemaker-Levy 9B and so on, was 450 kilometers across and had a mass of up to 10 million metric tons. If you remember Chelyabinsk 2011, where a meteor exploded over Russia, you'll know that when small meteors like that enter the atmosphere, they tend to explode, generating an airburst dealing devastating damage through a shockwave. Whereas the meteor that exploded above Chelyabinsk had only been about 20 meters across at most, Shoemaker-Levy 9A was 22 times larger than that, and as such, did not immediately burst apart when it entered the Jovian stratosphere. As it slammed into Jupiter's upper atmosphere with a speed of 60 kilometers per second, it generated a fireball which Galileo measured reached a peak temperature of over 24,000 kelvins, indicating deep atmospheric penetration. The plume of the fireball quickly rose to a height of 3,000 kilometers, which was high enough to peak beyond Jupiter's far side, and was thus observed by Hubble all the way from Earth. This image by Hubble shows in low resolution what might have been among one of the most powerful explosions ever glimpsed by humanity up to that point. Despite their predictions, astronomers had not expected the fireball to be so great it could be seen from Earth, and as such had no idea what to expect with regards to the impact site's visibility. When just minutes after the impact, Jupiter's fast rotation rate brought the impact site within view of the Earth, what revealed itself was a massive crescent-shaped dark spot the size of Egypt. Just 6.5 hours later, Fragment B, which was about the same size and mass as Fragment A, crashed into Jupiter, generating another fireball and dark spot. And over the next few days, the fragments would continue hitting Jupiter one after the other. As the fragments sometimes varied immensely in size and mass, each impact was different. For example, Fragment D was a sizable one, measuring over a kilometer across, and thus the fireball and dark spot it generated were much larger than, for example, Fragment F, which was a much smaller chunk, and its impact was barely detected at all. One of, if not the largest impact, was that of Fragment G, which measured well over a kilometer across and was over 50 times as massive as Fragment A had been. When Fragment G crashed into Jupiter in the early morning of 18 July, its kinetic energy was so great that it released an estimated force of 6 million megatons of TNT, which is roughly 200 times as powerful as the 1815 Tambora eruption. Its fireball was so bright, it was not just visible from Earth, but briefly outshined Jupiter itself. The dark spot it generated was estimated to be up to 12,000 kilometers across, large enough to fit the whole Earth inside. Some fragments, like Fragment J, disintegrated before impact and produced no discernible impact features at all. Other fragments, like Fragment Q, were clusters in and of themselves, likely having fragmented further after the initial 1992 Jupiter approach. consisting of a diffuse debris field rather than a cohesive chunk. As the Q cluster impacted Jupiter in the evening of 20 July, the event was spread out over a 26-minute period, during which the cluster's fragments impacted the planet one by one. Despite having originally been similar if not larger than fragment G, due to Q's fragmented nature, its impacts were more modest, each generating smaller fireballs and plumes, and leaving no single dominant scar behind. Finally, in the morning of 22 July at 8:15 UTC, the last of the fragments of Comet Shoemaker-Levy 9, dubbed Fragment W, plunged down into the Jovian atmosphere, and with one final fireball producing a 3,000 km wide impact scar, it was finally over. And while some smaller undetectable fragments or dust may have trailed behind, they would produce no more fireballs, no more plumes, and no more scars. Comet Shoemaker-Levy 9 was finally gone. As the fragments had hit Jupiter at such incredible speeds and upon impact heated the atmosphere to several tens of thousands of kelvins, they had triggered various shock chemical reactions in the atmosphere. For example, the impacts produced hydrogen cyanide, polymers, and tholins. These chemicals appear much darker than Jupiter's ammonia clouds, and as such were primarily responsible for the previously discussed dark spots. The dark spots from the impacts persisted for some time in the Jovian atmosphere. While the smaller spots, like that from fragments A and W, vanished beneath Jupiter's zonal winds in just a few weeks, larger ones, like those from fragments D, G, or L, persisted for months before dispersal. As these spots dispersed, they provided crucial insights to how wind patterns work on Jupiter. To the surprise of many scientists, the impacts had not produced much sulfur dioxide. Up to that point, it was assumed both Jupiter and comets like Shoemaker-Levy 9 were relatively oxygen-rich. But since only minute amounts of sulfur dioxide were detected post-impact, it revealed both must have been much more poor in oxygen than previously thought. The impacts had also propelled ammonia much higher into the Jovian atmosphere than normal. While we already knew Jupiter's clouds are mostly made of ammonia, this revealed that below the clouds there exist further ammonia reservoirs, which got splashed up by the impacts. Scientists were able to detect elevated ammonia levels until late 1995. This, however, was nothing compared to the water. As icy bodies, comets are naturally rich in water, and as such, the impacts provided a fresh injection of water into the Jovian atmosphere. This water proved to be extremely long-lived and remains detectable up to this day, 32 years later. According to ESA, as much as 95% of stratospheric water on Jupiter originated from Comet Shoemaker-Levy 9. Before the Shoemaker-Levy 9 impacts, astronomers had already theorized about Jupiter's strong gravity well, acting like sort of a cosmic vacuum cleaner for comets and asteroids. While simulations had supported this view, it remained without observed evidence. But then, the world watched in awe as Jupiter tore a comet to shreds and swallowed it whole, presenting undeniable proof of the theory. Today, we know that impacts like those of Shoemaker-Levy 9 are far from rare. In 2009, for example, another big impact hit Jupiter. Unlike with Shoemaker-Levy 9 though, this impact was not anticipated, and as such, we only saw its aftermath. A dark spot the size of the Pacific Ocean. Whereas we had known about the Shoemaker-Levy 9 impacts in advance, we never saw what hit Jupiter that day coming. Though based on the singular impact feature it left behind, it was likely only a solitary object measuring less than a kilometer across. But even fragmented impacts like those of Shoemaker-Levy 9 are not thought to be unique. While unseen in our time, on Jupiter's moon Ganymede there's a crater chain called Enki Katana, consisting of 13 craters that formed almost simultaneously. The prevailing theory is that this impact structure was formed by a comet that was fractured into pieces much like Shoemaker-Levy 9, but instead of hitting Jupiter, it ended up crashing down onto Ganymede. While dating extraterrestrial impact features is difficult, based upon the surrounding terrain, Enki Katana is likely geologically recent, showing that these sorts of impacts might be more frequent than we think. In its destruction, Comet Shoemaker-Levy 9 allowed us to refine the orbital models for comets, showing how Jupiter can perturb them over time, capturing them, ejecting them, or breaking them up. It is estimated that Jupiter experiences 12 to 45 impacts by objects larger than 10 meters annually. That would translate to an impact rate roughly 2,000 to 8,000 times greater than that of the Earth. Today, the prevailing analysis is that while events on the scale of Shoemaker-Levy 9 are a bit more rare, Jupiter regularly devours space rubble, serving as sort of a comet filter for the inner solar system. While it's true that in the majority of cases Jupiter serves as the protector of the inner solar system, substantially reducing impact risks by as much as 95% for the Earth in some models, simulations also prove it's capable of hurtling comets towards the inner solar system. For a deeper analysis on the exact mechanics driving Jupiter's comet shield, I will leave an info card to Brain Truffle's video on the subject, which goes into much more detail than I'm able to do here. So while Jupiter protects us from the bulk of impactors, we're not 100% safe, and something like Shoemaker-Levy 9 could indeed one day hit the Earth. Eugene Shoemaker had been a pioneer in taking impact risks seriously, and the events of July 1994 proved to everyone beyond a shadow of a doubt just how big of a risk impacts can pose. In that spirit, Shoemaker-Levy 9 ended up serving as a real wake-up call for planetary defense, a term virtually unknown previously. In 1998, 2 years after the impacts, NASA was directed by the United States Congress to catalog all near-Earth objects larger than 1 kilometer within the next 10 years, something Shoemaker had often argued for. As of today, it's estimated 95% of those objects are now known and cataloged. Unfortunately for us, none currently seem to pose an acute risk of Earth impact. While that takes care of the apocalypse impactors, objects smaller than 1 kilometer could definitely still cause regional devastation, and as such, ongoing efforts aim to catalog all near-Earth objects over 140 meters, which, if successful, would substantially reduce the number of possible catastrophes. But these efforts are still ongoing, with only about 40% of them cataloged today. While early detection is our main plan for planetary defense, in 2022 NASA successfully carried out the Double Asteroid Redirection Test, or DART for short. DART was the first planetary defense test and saw NASA slam a probe into the 160 meter wide asteroid moon Dimorphos to alter its trajectory. The impact successfully shortened Dimorphos' orbit by 32 minutes, far more than the predicted 4 minutes. Thus, DART proves humanity now has the capability to alter asteroid paths, enabling a new key tool in planetary defense. Granted though, this would not really work for larger asteroids, or ones that manage to sneak up on us, like interstellar visitors to our solar system. But our abilities continue to advance, and we are already in a much better position than we ever were in 1994. I did a full video on asteroid defense all the way back in 2018, and it's awesome to see our abilities have advanced even further since then. Where in the 90s our options to defend the Earth from a potential impact were practically non-existent, today we're actively monitoring potentially hazardous asteroids and have at least some limited capabilities to respond to smaller impactors, provided we can detect them early enough. And a lot of that can be attributed to efforts made in light of Shoemaker-Levy 9's impacts raising awareness to this issue. While a lot of process is definitely still to be made, we can sleep a lot easier now than Mr. Shoemaker ever could back in the 70s. Unfortunately for Mr. Shoemaker, he would not live to see any of these achievements. In 1997, while on a field expedition to Australia together with his wife Carolyn, their car was hit by another vehicle, killing him instantly. The following year, NASA honored him by sending some of his ashes aboard the Lunar Prospector mission to the Moon. And to this day, he remains the only person buried on another celestial body. Carolyn, on the other hand, did survive the crash and will continue to work at NASA and discover comets until her death in 2021 at the age of 92. Today, she is credited with the discovery of at least 32 comets. David Levy is still alive, continuing his work as a science writer and comet hunter, authoring many books, including the book Shoemaker by Levy, The Man Who Made an Impact, a biography of his friend and longtime collaborator. Ultimately, Comet Shoemaker-Levy 9 went down in history. Its bizarre, fragmented nature shocked its discoverers, and when it became known it was due for Jupiter impact, the whole world tuned in as 21 unbelievably violent impacts struck Planet 5. Its impacts, although having faded from public memory, raised awareness for planetary defense in a way nothing else could have. It even left a cultural impact, as throughout the 90s it also inspired many asteroid disaster movies such as Armageddon and Deep Impact, with Eugene Shoemaker even serving as a scientific advisor for the latter. So I really hope you enjoyed this video. If you made it all the way to the end, leave me a like and maybe consider subscribing. It really helps me out, and I do all kinds of science videos and world building on this channel. So if that's something up your alley, stick around and subscribe. As always, thank you so much for watching, and I hope to see you guys in the next one. Ad Astra.